So first of all, I just want to say thank you all for inviting me for this opportunity to discuss building institutional capacity for STEM at under-resourced HSIs. And so just as a brief overview and outline, I'm going to be discussing, first of all, the importance of STEM education at HSIs. I know we all know that, but it's always good to make sure that we all have working from a similar background, some of the challenges to enhancing capacity, STEM education, developing institutional buy-in, strategies for augmenting experiential learning in STEM, and then developing a plan. So first of all, I just want, of course, again, everything that we know, the STEM workforce is not very diverse. If you take a look at the US population, it is becoming more diverse. In 2000, about 12.5% of the population was Hispanic. That moved up to 18.7% in 2020. And it's estimated that by 2060, 27.5% of the population is going to be projected to be Hispanic, more than a quarter of the population. And so that's a huge portion of the people who are going to be Americans. However, what we're seeing is that diversity in STEM itself isn't really changing all that much, and it's much lower than what the population should suggest. In 2021, Hispanic workers made up only 8% of STEM occupations that required a BS. 17% of the STEM BS degrees were awarded Hispanic students. That shrinks when you take a look at the master's, which is only 13%, and it drops even further with 9%. So again, we see that even though the population is increasing, the number of STEM graduates with degrees that are going to be fulfilling the workforce is much lower than what we're seeing in the population. And of course, why is that important? What's the impact of that? Well, of course, we all know that it's important to have different perspectives when we're approaching a problem. Different perspectives, different backgrounds allow for a more unified approach to addressing a problem, because the more backgrounds you have, the more perspectives you have, and the greater the problem solving can be. Also, it's important in increasing public trust in the research and in STEM. We all know that there are certain populations that have a distrust of scientists, distrust of doctors, and part of that has to do with history, but another part that has to do with the fact that they don't see themselves in those positions. The more of us that are in STEM positions, the more of us that are in physicians' positions, the more of us that we can be seen, the more trust we'll have amongst our populations. In addition to that, there can also be serious repercussions to this lack of diversity. This is especially when taking a look at healthcare and healthcare disparities. The research has shown that there are differential outcomes and differential treatments based upon race throughout the different populations. So it's important, again, to have that diversity. It's also important in terms of preclinical and research trial biases. An interesting statistic is that leading up to about 2018, 78% of the people who were used in doing experiments with genetic studies of diseases were of European descent. They actually only make up about 16% of the world population. So this small population was overly represented in these trials, and those trials can have huge impact. So for example, 67% of the Puerto Rican children do not respond to drugs used in asthma inhalers. Again, if you had a broader base of participants, things like that would have been caught earlier. Up to 75% of Pacific Islanders can't convert a specific antiplatelet drug, which means it's useless to them. And again, having a broader base of subjects in these trials would have addressed this problem. And again, the idea about having a broader base will come from the fact that you have a broader population of researchers who will be taking that into consideration. I just wanted to dip a little bit into the importance of basic research, because again, the idea of having a strong STEM educational infrastructure is based upon the idea that people value STEM science and STEM research. And so the importance of having basic research is that we all know breakthroughs come from foundational knowledge. Most of the things that we have that we consider to be important to us in terms of science technology weren't developed because that's what they were looking for. It was developed because of a side project. Examples would be MRI technology, which had an idea of being used for studying molecular structures. The drugs such as cisplatin and olaparib were discovered doing, again, basic research. However, now they're being used as cancer treatments. But the problem is that there's a huge public misconception around the importance of basic research and importance of supporting research at the university. These are just a few of the headlines from the last 10 years or so that show that really public support of basic research is under attack. From the Hoover Institute, investing in bad science, dubious projects of government agencies. From the Cato Institute, federal science funding won't accomplish anything the private sector can't do better. Or from Forbes, most government-sponsored research is simply wasteful. So with all of this out in the public, it's not all that surprising that support for research and support for STEM education is not as strong as it should be. It's also made worse when we have public politicians such as Rand Paul coming up each year with wasteful spending, right? And so these are some of the ones that I've chosen from the last few years. He talked about a $1 million study on the sex lives of fruit flies, or $6.97 million to create a smart toilet, or $1.3 million to study whether people eat ground up bugs. And on the face of it, it sounds ludicrous, ridiculous. But if you take a look at what that research is actually doing, you see that it actually does have real impact. The sex lives of fruit flies, that's actually looking at the neurocircuitry of reward-seeking behavior, which of course has an impact on understanding drug and alcohol addiction and potential ways of treating it. The smart toilet actually was an automated way of doing early detection of cancer. And we all know that early detection is the best way to have better results from treatments. Finally, the study on whether people will eat ground up bugs really was a feasibility study of using insect protein as a food source, which is eco-conscious. And so again, it's important that we make sure that these misconceptions are addressed. In addition to the public issues around investing in STEM education, there are also the institutional concerns and roadblocks. So one would be limited administrative or faculty support. Administrators, speaking as one, we are concerned about a lot of things. There are a lot of things on our plates, mainly around student success, around retention rates, around balancing budget, around graduation rates. And so sometimes things that are important to us don't really rise above the background. The same thing can happen with faculty between teaching and trying to do the scholarship and trying to address the learning problems from the pandemic. Faculty have a lot on their plate. And again, it's very difficult for them to think about the importance of STEM education and enhancing it. Oftentimes, in some of our institutions, we have inadequate facilities, whether or not it's a matter of the buildings being old or not having up-to-date equipment or not just having the lab space. These are all problems that seem somewhat insurmountable when you're trying to expand your STEM educational base. Lack of necessary funding, of course, a lot of changes require money. Getting that money is often difficult. And then there are also the student external commitments. A lot of students, especially at minority-serving institutions, have other things that they have to deal with aside from their academics. They have responsibilities with family that often take a lot of time, which makes it difficult for them to realize that improving STEM education is important. So how do we go about addressing these things? How do we, for example, go ahead and get institutional buy-in? Well, one thing is to tie in STEM education with the college's mission statement. All of our colleges have mission statements, and all of them have something around student success. So it is, or should be, relatively easy to tie STEM education directly into that. And that, again, is a very powerful tool when you are speaking to your administration, when you're asking for them to provide resources to support your projects. It's important to link STEM experiential learning with improved retention and graduation rates. There's a plethora of data out there that shows that students who get into the lab, get mentoring, they're the ones who have higher rates of being retained at the college, retained in STEM fields to begin with, and then of course graduating and having successful careers. It's important to convince faculty that STEM experiential learning can support their scholarship. Again, having students working with them, oftentimes faculty feel that as a drain on their resources, a drain on their time. When in reality, once they are trained, those students can produce a lot and can help advance their research agendas. Demonstrate that STEM experiential learning can lead to paid internships for better jobs. Again, this is focused more towards the students. So when the students are thinking that I don't have the time to work in a faculty member's lab, it's important to make it clear to them that this time is an investment. It's not a waste. It's an investment that will allow you to get that paid internship, which will allow you to get that better job coming out of college. So again, getting that buy-in from all constituencies is really, really important. So again, as there are a number of ways to help build institutional capacity, one of the most tried and true ways is through cures or course-based undergraduate research experiences. So just out of curiosity, how many of you have taught a cure? Right, so there are a lot here. So this is really good because when it comes time for the discussion, these are the experts that we can ask questions of and get what they've learned, what worked, what didn't work. So thank you for doing that. But the idea behind this is that for those of you who haven't done it or might not know it, is that you actually introduce research units into courses. The idea being that students take a research project, very limited of course, from hypothesis testing to developing experiments, performing and collecting data, doing the analysis, and then coming to conclusions based on that analysis. And so what ends up happening is that students gain the content knowledge from the course, as well as technical skills that will be useful later on. They show that they have improved academic and professional skills. That includes not only being able to understand and make judgments, but also skills such as public speaking, writing communication skills, which are also really useful everywhere else. There's improved confidence and self-efficacy. The great thing about this is that there's no extracurricular time required. Since these are embedded in courses, those students who have other commitments are still getting this experience. And then, of course, again, the improved retention and graduation rates. The faculty in college also benefits. One is that with the CURE, there's no additional time commitment for the faculty member. The faculty member is going to be teaching that course anyway. Now they're able to just teach that course or have a little bit of a different bend to it. And there are no additional costs, or at least limited additional costs, in that the school's already going to have to pay for the reagents for that lab course. Now it's just a shift in what reagents are being bought and what they're being used for. Cures basically fall into two different types. They're the pre-designed ones, and then they're the homegrown ones. And so for the pre-designed ones, there are a number of them out there. I've just listed two of them. One is a Small World Initiative. This is about crowdsourcing antibiotic discovery. In this one, the students actually go out, they collect soil samples, they isolate bacteria or other microbes, and look to see whether or not they produce antibiotics. If they do, then they actually do some genomics, identifying what the microorganisms are, and they can also do some chemical analysis of the antibiotic itself. So it spreads across a number of different disciplines. And again, the students are going from the very beginning to the end of the project. Another one is C phages. In this case, they're identifying novel phages. Again, the students go out, collect soil samples, identify the phages, and then do bioinformatics to identify them. The great advantage of these is that they're plug and play. They've already been developed, they've already been workshopped, they've already had all the bugs worked out of them. And so you literally, all you have to do is take them and plug them into your course. The downside to it is that it does require training. Oftentimes the groups that do this, they want you to go and do a workshop with them. And that, of course, is added time and money for the faculty member that wants to do it. The other option is to do something that's homegrown. And so this is something that is developed by the faculty member themselves. The great thing about this is that the faculty member can go ahead and incorporate their own research into the course that they're teaching. The advantage is that it's going to advance the faculty member's scholarship and that it's flexible. It can be done at any level, first year, second year, fourth year capstone. The disadvantage is that it requires modifying protocols for the students and troubleshooting. Protocols that we use in our own research are written in a way for people who are trained to understand it. This needs to be changed and modified for students to understand. And I just want to do a quick aside just to give you an example of this, is that in one science lab class I was teaching, the students were grinding up beef to isolate beef protein. And in the protocol, it said of their 500 milliliters of lysate to take 1 milliliter and save it for later analysis. So I had one pair, they took their 1 mil for later analysis and then poured the rest of it down the drain. So things that you don't think you have to mention, you kind of have to think about. So I just wanted to give you a couple of examples of what I've done in terms of some of the homegrown cures. So what my work is on cell communication. Specifically, I work with a social amoeba called Dictylium discoideum. It's a cool organism because it has 2 different life cycles. One as an individual amoeba, lives in the soil, eats bacteria, divides by mitosis. However, when they run out of food, the cells start sending signals to each other saying that we're starving, and they come together to form a multicellular organism that eventually goes through development, forming 2 different cell types. And so I took my research and I applied it to 2 different classes. The first class was a 200-level cell biology class. So this is a class basically for students who had just finished their first year of general biology. So they had a little bit of knowledge, but not much lab experience or technique. And so what I did was I had the students characterize some novel cytoskeleton mutants that I had created in my lab. Again, the idea being that I created 3 modules. One where the students examined the cytoskeleton, second where the students looked at the ability of these mutants to chemotax, and the third to take a look at how these mutants developed. And of course, what I had to do is I had to replace 3 elements that were in that course before. And so to keep things consistent, I removed the cytoskeletal labs that had previously been there. Truthfully, I think that was probably a good thing because those labs were pretty outdated and hadn't really been updated for 20 years. And I believe that these were a better use of the students' times. And so what the students learned from this is to approach a problem through numerous techniques. They learned, they learned immunofluorescence, they learned cell biology, they learned developmental processes. And what was really great about this experience that I found is that the students then, after they did experiments, they then had to synthesize their work with the idea of having to take the fact that some of the ideas that they learned at the cell structure level had an impact on the cell behavior level and eventually the organism's development overall. So again, it helped the students connect these 3 different areas in their final project. And of course, the students ended up writing up their lab report in the form of a scientific paper. So again, reinforcing written communication skills. The second thing I did was for a capstone research project where again, students were given mutants, this time from a suppressor screen that I did. And again, they did a number of experiments, chemotaxis, extending cytoskeleton development, epistasis analysis, and then looking at autonomous versus non-autonomous behavior. And this time, the students had a lot more time to do, and so they were actually able to do multiple repetitions of the experiments to get replicate data. At the end of it, they ended up presenting their data in a scientific talk. And one of the things I want to talk about in terms of these 2 examples is how useful this was for me. So in the cell biology course, there were 180 students in that course. The students worked in pairs, giving 90 pairs. That means that I was able to give 10 mutants that I had to 9 different groups. That's 9 different replicates. That's a lot of work that I would not have been able to do myself. So when the students did it, I was able to take those mutants that were interesting and then focus my research on there. And they actually became the topic of some of the NSF grants that I applied for. So this is incredibly useful for a faculty member's scholarship. The other form of doing a cure is, instead of being embedded in a course, is to have it be a more intense workshop. So the idea being that you have the students for 2 to 3 weeks. The students learn a lab technique. Again, they develop the communication skills. And again, the faculty advance the research. The disadvantage of this is that this is an additional time commitment to the student, and there are additional costs. However, again, the way that you want to use this is going to be based upon what your students can or cannot afford to do. And then just an example of a workshop type we did. This was looking at the microbial population changes during sourdough fermentation. And in this case, what the students did was they took time samples of the growth culture and then basically did microbial analysis on it, either based on basic microbiology where they were isolating bacteria, purifying DNA, sending out for sequencing, or doing metagenomics. And so again, the students did a lot of work. They came with results. They presented their results in a poster session. Some of the outcomes, again, is that the students learned some basic skills that they learned and can apply to any biotech company that they'd be working at, either for an internship or for a job. Again, they have something to put on their resume to say that I did this project from start to finish, which is always important. The students, again, in terms of academics, were able to learn to link how fermentation process changes change the environment, which then allowed for different populations to either grow or decrease. Students learned poster construction and presentation, and several of the students ended up staying on because they were so interested to work in that faculty member's lab. And then this is just an example of one of the posters, just again to show that these were very professional posters and very professional presentations the students did. It was really impressive and very heartening. So we see cures are useful. We see cures can benefit. How do we go about doing this? So the first part is you need to build support. First thing you need to do is assess your institution's readiness. Where are they in terms of budget? Where are they in terms of facilities? You then, after doing that analysis, take a look at what the roadblocks could be and potential solutions. Next, you need to recruit interested faculty. There's always going to be some faculty out there who are going to want to be on board. You need to get that and form a coalition of the willing. And then you need to brainstorm ideas for research projects. In terms of choosing which projects you want to do, you really want to focus on projects that can capture the students' interest. These usually deal with somehow linking it to medicine or disease. So in my case, I linked it to cancer metastasis. Or you can do things such as climate change or social justice. All these things students are usually very interested in. You then need to decide what format you want to do, whether or not you're going to do a cure, embedding it in the course, or a workshop being extracurricular. And again, there's a question of what best serves your student population and what best is supported by your available resources. Then you decide on the length, whether or not you want to do one module in one course or multiple modules, of course, across multiple courses. The level, whether or not it's going to be introductory, which is great because you can capture the students early. The difficulty with introductory ones is that students lack knowledge and lack skills, and so it's a little bit difficult. However, if you do upper division, the students are better prepared, but you may have lost some of the students along the way before they got there. And then once chosen, do a small pilot. Do one section of the course, work out the bugs before you expand. Of course, the perennial question is funding. There are some no-cost options. One of those being public databases. There are public databases out there that have tons of information around disease prevalence, air and water quality, flooding maps, snowfall, rainfall. These are great because what you can do is you can use the information from the specific area that your college is in. And that provides a direct connection to the student when they see, oh, this is my zip code. This is what's going on. And so you can use those data to design an experiment where the students, while they aren't actually collecting the data, they are going out into the databases and capturing those data, still doing the analysis and still drawing the conclusions. Developing plan funding. As you all know, there are tons of federal funding agencies out there, NSF, Department of Education, NIH. One that you might not know so much about are the congressionally directed spending, or what's called earmarks. I have found this to be incredibly useful. In the last 3 years, my campus has been able to get about $4.5 million to support purchasing of equipment, to support paying students to do research, to support faculty training. It really is all senators and all Congress people have these. They are worth looking into. They usually start asking for proposals around February or March. So next year, it's a little bit past time. Next year, definitely look into this as a source of funding. There are private institutes such as Howard Hughes Medical Institute. And then the key to all of these is, of course, if you've run these pilots, to use the data from those pilots and have a very robust assessment proposal for process for the proposal. And then these are just some of the resources that are out there around cures. The one from the University of Texas, Freshman Research Initiative. This, if you're only going to look at one site, look at this one. This is amazing. They have set up a system whereby every single freshman student gets a research experience. They actually take the students and divide them into sub-areas based upon their scientific interests. Phenomenal. Carleton College CureNet. This is kind of a repository of different cures out there. This 2019 article, Fear of the Cure. This is kind of a nice step-by-step protocol for developing and implementing cures. And then Teach the Earth, which is a set of cures based on earth science. And with that, I just want to thank you and ask if there are any questions.